Today is the beginning of linear programming and duality. So in this lecture, we will talk about what is linear programming, what is LP, why do we study it, and we're gonna learn like a kind of LP language, a bunch of terminology, and the concept of duality. Actually, there is just no algorithm today. It's just to learn the concept, but it's still important because basically kind of everything after this class, like throughout the whole, like the second half of this semester, we will kind of base ourselves on LP quite a lot. Okay, so we need this language. Yeah. Okay, but let me start with some small example. One sec, it's not like looks not nice. Let's see if I can make it nicer. Try again. Okay, anyway. It's a bit blurry, but should be fine. Okay. Just to motivate what is LP, right? Like imagine that you are like a baker with some limited resource, like you have 2 units of flour, like 6 units of sugar, like not too many like resource that you have. But you want to maximize the benefit, the money that you want, that you get. Now there are like, let's say there are some constraints. Like you can choose to make cake and it sells like a $3 per unit. But to make a cake, you need, to make 1 unit of cake, you would need 2 units of flour and 3 units of sugar. Also, you can choose to make cookie, which is like worth this much, 2 units of, like 1 unit you get $2. And like for each unit of cookie, you need to pay like one flour and 4 sugar, like just some constraint, right? And okay, the question is basically, what is the fractional units that you should like within this budget? How much you should make cake and cookies? That's the question. Okay. And okay, you don't need to calculate this, but my point is that the question can be formalized mathematically in terms of something that we call linear program. How? You can say it like this. You can write it like this. That is, let's say that x1 denote how much you make cake and x2 denote how much you make cookie. Okay. So we want to maximize money. So for each unit of cake, you get $3. So you want to maximize this 3x1. And for each unit of cookie, you get 2. So plus 2x2. So whatever unit that you make for cake and cookie, this is the money that you get. You want to maximize this. And now, okay, but we have like a budget. We have like some limited resource. For flour, you have at most 2 units of flour. So now try to capture this. Just say that, okay, for each cake, it takes 2 units of flour. For each unit of cookie, it takes 1 unit. So that gives you 2x1 plus x2 is at most 2. Okay. And do the same for cookie here. It's 3 here and it's 4 here, so it's 3 here and 4 here. And you have at most 6 units of sugar, so at most 6 here. Okay. And also, by the way, like we didn't say this in English, but you need to put it in math. That is, you can only make positive amount of cookies or positive amount of cake. Okay. Do you agree that this expression now capture the question that we want to solve? Okay. So this is basically one instance of linear program. Okay, like write down the objective and write down a bunch of constraints. Okay, good. You can look at this in like in a geometric way too. So if you look at the constraint for flower, which is gonna be this one. This is like you can create like a graph here, right? Where this is like excess of x1. This is for x2, and this inequality basically gives you this constraint, saying that you need to be on the left of this constraint, because beyond this it's kind of the point x1 and x2 when you don't have enough flour. Another constraint for sugar is here. Everything needs to be below this. Only point below this thing is like respect the limit of your sugar. So with these two constraints, it basically gives you the intersection of these two constraints. It gives you the feasible region. This is like the place, the purple place is here. It's just the place where like you can choose to make amount of cake and cookie, but within this purple region, you have enough resource. Okay. And so like the purple region is the place where this constraint is satisfied. Okay. But now if you want to maximize money, then you can also write down it's like an objective like kind of the direction. Okay. And like the objective basically gives, if the objective is just x1, suppose it's just x1, what would be like the direction of this objective? Just go this way, right? If it's just x2, then it's just go up. But now like the objective is like this, so it's kind of in between. And basically it says that with this objective, you want to go as far as possible in the objective direction. So what is asked you is just like try to find a point in this feasible region that go as far as possible in this direction, in the objective direction. And you can see that from this region, the point that maximize, like that go further in this direction, in the objective direction is this point. Because if you, for example, like project this down to this direction, then it go furthest. If it's this point, for example, if you go down here, then it's just this point. It's not as far as you can. So I hope you see this geometrically, that linear program is like, you can view it in a geometric way. It has some feasible region and some objective direction. And you want to find the point in feasible region that go as far as possible in the objective direction. And in this case, you see that, okay, this is a point here, and it means that the best way is to make this much cake, this much cookie, and you get $3.6. Okay, so just some example. So now I think I'm ready to tell you what in general is linear program. It's just like the case when you have like n variables and m constraint. Think of variable as like the choice of cookie and cake and ice cream and so on. Like the choice that you can make for each, like what are the choices that you can make. And the constraints are like all kind of constraints that can happen. And basically the linear program is just this. It's any problem that you can write in this way. That is, you want to maximize some linear objective, like x times some like all the xi times some ci, sum of that, and you have like m many linear constraints, okay? And all the x's are positive. Okay, so the x are variables and like the coefficient a and b here and c are given, and you want to find x that is the best, that maximizes this thing. That's linear program. Okay. And the reason why we call it linear is because you see that each of the constraints here is linear. It's like it's a linear inequality. Like there is no x squared, there is no x cubed. Okay, there is no x1 times x2. Like the degree of x is just 1 for each term. And also here is linear. So both objective and constraint are linear. That's why we call linear program. And with this, you can write it in a succinct way. That is, I just think of this thing. Think of x as a, okay, I just put it here. Yeah. If you think of x as like a vector that encodes x1 to xn, c is a vector that encodes c1 to cn. It's just the inner product between x and c and x here. And okay, you want x to be positive here. This means that for every x I is positive. It's not negative. And b you encode it into like a vector of m dimension, not n, m. Okay? And a is just like a matrix of size m by n. And then you can encode this whole inequality succinctly in this way. Make sense? Question? Yeah.
Can you just explain what C is again in that bottom example quick? I just
C is this C is just like a vector like that encodes C1 to Cn. It's n-dimensional vector.
Mm-hmm.
So when you do inner product of C and X, you get exactly this thing.
Okay.
And what do you have when you have A times the matrix A times X, right? You matrix A, if matrix A is like this and X is like this is like n dimension, this is m dimension, this is n. When you multiply A to X, you basically get like the first row here is like, it's just, if this is A1, A2, like if I encode each row of A as, like if I say A1 is the first row of A, then this first, when you multiply X to A, you basically, like the first row, after multiplying, you get this thing, right? You see this, I hope. It's just how to write it in a succinct way. Okay? And this is called the standard form of linear program. Okay. So this standard form of linear program is actually very expressive. And let's see an example. Okay. Okay. So you have variable x, and you want to maximize this, which is c times x, right? With this constraint and with this like positive constraint. This is a standard form. Okay? But what if we want to capture something that is not quite standard form? I claim that we can still convert it to standard form. For example, what if you want to minimize the objective instead of maximize? Can you write it down into standard form still? Any idea? Any suggestion? Yeah, Blake?
You can multiply the objective function by -1
Exactly.
and minimize.
Exactly.
It'll be different by a sign.
Yeah.
But it'll be the same value.
Right. So if I want to minimize, then I say that I want to maximize this thing. Basically, replace each of the ci by minus ci. And that is just to minimize. It's the same as minimize this thing. Okay. That's fine. Minimize and maximize, you can put it into the standard form. Okay, now back to maximize one. But what if this constraint, I want to get at least instead of at most. Like it used to be at most, I want at least. What to do? Yeah.
Multiply by -1.
Yeah. Again.
Yeah.
Just multiply by -1 again. Yeah. And now it's in the standard form. Okay. What if I want equality? Yeah.
Have a less than or equal to and a greater than equal to for the same.
Exactly. Yeah. Put both greater, like at least and at most. Put both constraint there. So put both of this there, and you know that this one you can make it into like a standard form. So it captures equality as well. Okay. So the next one is less trivial, more challenging, but it's still, let's see if you can do it. Like I used to have all the xi are positive, like non-negative. Now let's say I want to drop that x1 is at least 0. I allow x1 to be negative or positive, doesn't matter. Can we solve this? Can we like show the standard form LP that still capture this?
So what does it mean by all variables are non-negative if x1, one of the variables? Does it mean all other variables be non-negative? Or
So I mean, I want to create another LP that is in the standard form that is equivalent to this one, and in the new LP, all the variables there are non-negative.
Without the non-negativity constraint? Without the final constraint?
With the final constraint.
Oh, so you only want x1 not to be constrained.
Okay. Actually, it doesn't matter too much. Let me just tell. It's because it's not the point. So you see that when I create, let's say I create this two variable here, x1 prime and x1 double prime, and put it like this. Okay. Now this is in the standard form. You agree? Because all the variables are non-negative. But it's basically equivalent to drop like a x1 from here. Because if I need that x1 need to be actually negative, then I just gonna put, like if x1 need to be negative 10, let's say, then I gonna put x double prime here to be positive 10.
Yeah.
Then it's gonna like act like x1 when x1 is negative. Yeah.
doesn't this mess up our like dimensionality though? Because now we have more variables than we have multipliers.
Oh, like there's no constraint that m and n need to be the same. There are n variables, there are m constraints. M and n can be anything. Doesn't need to be the same. So this one like increase the number of variables by 1, but yeah, the number of constraints and variables can be anything anyway.
How are the two new variables being related to the original x1? Because in our objective function, we have in the maximized up top, you have
good.
x1,
So
but they're not.
This one should be replaced too. It should be replaced by x1 minus x1 double prime.
Okay.
Okay. Questions?
I see.
Good. So so the point is that we can kind of just focus on the standard form because it's quite general. Like as long as your constraint and the objective is linear, even if your constraint is at most or at least or inequality, or you want you to drop some of the xi at least 0 here, you can still like capture it with the standard form. Okay. Like with all above chains here, like it's still called an LP, and you can make it in the standard form, even if it's not in the standard form. Okay. Okay. So you see soon, like I hope you can imagine that like many things can be modeled as an LP. Like the first example that you see, the bigger thing, and you're gonna see that max flow can be more. It's just captured by LP as well soon. Okay. Now, okay, LP is super expressive, but it turns out that given anything that you can write down as an LP, you can actually solve it in polynomial time. So this is the theorem saying that there is a polynomial time algorithm for solving any LP. Okay. And like there was like a practical algorithm called simplex discovered a long time ago. It's really fast in practice, but actually can be slow, like in the worst case. But it's used a lot in practice. Now there is a new algorithm, like another algorithm called ellipsoid, and then interior point method. This one is fast in practice and also polynomial time in theory as well. Okay. But this is not the scope of this course, like how to solve LP in polynomial time. I will not talk about that. If you want to learn, then there are many online lectures, and also this course is like have a nice lecture note. Okay. So you can go there. But okay, given that you know that any LP can be solved fast, you can see that the application, like this follows to many applications. You can use it to solve many day-to-day life problems, like to design new plans and so on. But actually, it's used a lot in scientific computing. I don't have like a concrete example, but I hope you can imagine that LP is so expressive. It can capture so many things. Okay, but let's see one non-trivial example. I want you to see that like max flow, the problem that is actually quite expressive itself, right? Like once you can solve max flow, you saw before that we can solve like 10 many other problems. It is actually can be modeled as an LP too. Some LP is even more expressive than max flow. So how do you write down? How do you model LP as a max flow as an LP? Okay. Anyone recall what is a flow? There are two constraints for a flow to be a flow, to be a valid flow. What's the two constraints about flow?
The flow can't exceed the capacities on every single edge, and nodes can't leak any water, or like the water coming in has to equal the water going out.
Exactly. So the first is capacity constraint. For each edge, the flow need to be at most the capacity. The second is flow conservation. For every node that is not sort and sink, you need that in and outflow must be the same. Okay. And what do you want to maximize?
The like inflow to the end.
the inflow, or like the total net.
Yeah, the total
Net
flow
flow.
going into T.
Yeah, exactly. Good. So like the total inflow minus the total outflow at T. Okay, so let's try to write down its SS and LP together actually. Okay, so if I have a graph, okay, and with this, which is like this, okay, good. And we basically gonna have a variables FE for each HE. 1 second, something is not good. Okay. For each HE, I have this variable FE, and FE should be positive. This is like just the flow on each edge, right? So now, maybe I just write it here. Okay. And then FE should be at most somehow. Okay. FE is at most CE for all E. This is just a constraint, capacity constraint. And we also know that have that for every node, which is not S and T, we have that a sum of F X to V for every edge X to V in E need to be equals to the sum of V to X V to X V to X Vx in E. Something is wrong. Okay. And what do we want to maximize? We can set like the net flow out of S too, right? Which is sum of Sx from minus xs. Okay. You agree? This is just like, it's just what MaxFlow is about, and it's just linear program. You can make it, like, how can you make it into the standard form? Well, you need to move this thing to another side and make this like a at most and at least, like the trick that we see. This is already good. This is good already. So that's it. Yeah. So the powerful MaxFlow is just like some special case of linear program. Okay. So here's like the reason why we study linear program. Well, one is just okay. It's a powerful black box. You know you can solve it fast, like in Poly time, but I will not teach it in this class. And so you can use it as a black box to solve many problems, like MaxFlow, and so on. But the point of this course is about the other two reasons, actually. It turns out that LP is like a tool for designing algorithm. It's like a tool for your thought, for your thinking. It's actually a way, it's like an algorithmic paradigm, similar to dynamic program or divide and conquer. Once you learn about this language and the concept, then you it's like a starting point on how to even design an algorithm. Also, it's a tool for proving theorem, not even about algorithm, for proving something in combinatorics, many things. This is, if you might not know what it means here, but think like you learn about Maxwell-Mincutt theorem. It's just some graph theoretic theorem. And then it can be used to solve, like to prove Hall theorem about matching, to prove Menger theorem about disjoint path. Okay. LP will have like a same flavor but more powerful. Okay. It's like a tool for like a toolkit for your thinking. So that's the point of this class. Okay. I hope you like by the end you can use LP as a tool for thinking. But to do this at all, you need to learn like more language and the concept of LP duality. Okay, so let's do it. So let's try to look at this LP in a geometric way. Okay. So again, X is variables, which is like a point in n-dimension space. Okay. And A is like a constraint of like there are m many constraints. So B is like a here. So there are B is like a vector in m dimension with m dimension too. Okay. So the way you should think about this is the following. For each constraint J, if A is like AJ is like the jth row of A, then AJ times X at most BJ is like the half space. Half space is what? It's just like if you look at AJ times X equals B, it's like some hyperplane on the space, right? This is like a hyperplane. And when you look at most B, it's just like look at this hyperplane and take one side of a hyperplane. It's just like you look, when in two dimension, it's just a line. This is a hyperplane, and this is just everything on one side of the line. It's half space. And you have several constraints, basic, and you need to specify every constraint. So it's like an intersection of half space. This is the feasible region. Okay. And there is a name for the intersection of half space. It's called polyhedron. Okay. That's just a name. Okay. So this intersection of half space is just what we call feasible region. And like there's something called vertex, which is just kind of, I will not define it mathematically, but it's just from the picture, it's like the corner of this intersection. Okay. And you can have one objective function, which is like just to say in which direction you want to go as far as possible. And in this case, the optimal point is just the point in feasible region that go furthest in the objective. And this can be unbounded, right? If actually there is another constraint like this, then it's bounded. Okay. And at least the way I think about it is like the physical interpretation of LP is that like you can think like objective C is like the direction of gravity. And you can imagine that you drop, like you have some ball in the feasible region and the ball just like kind of follow the gravity. And where does it stop? Basically, it's just gonna stop at the optimal solution. Okay. Can there be more than one optimal solution? It can. For example, if actually there is another constraint like this, that is just like kind of perpendicular to the objective function, then everything on the on this will be optimal. Okay, so feasible region, this thing is called polyhedron, yeah. Can be bounded or unbounded. And so there can be possible outcome of linear program. One is that, okay, optimal solution exists, the ball stops at some point. It can be that it's unbounded when you try to optimize, and it's unbounded because you want to optimize on like the direction that is infinite. So the ball never stops. And it can be infeasible too. That is, actually the feasible region is just empty. That can happen. How? Well, like if I say I have another constraint saying that, well, everything needs to be below this thing, then there is just no feasible region. Okay. Can you tell me which one can be a valid feasible region of LP? Like from these three. Can this one be a valid feasible region?
Yeah.
Yes. Yeah. How about this one? Yes. It can be unbounded, that's fine. How about this one? Why not?
1, 2 half spaces. It would cut off.
Yeah.
Like it would cut off.
Yeah, if you have this constraint, it means that you should have like, you have should have something like this. So anything here cannot be here. And also if you have this, then everything here cannot be here. So like it should be just in this region. That is a feasible region. So the picture should be like the set here should be basically convex. Yeah, that's like, so linear program is the part of convex program. But if you know about this word, and convex program can be so like you need that the set is convex to be able to solve it fast. Yeah. Okay. Okay, so this is good, this is not. So let me go to next concept of duality. So if you have this LP, okay, and suppose that, let's say I don't want to solve the LP exactly yet, but I just want some certificate that I can check quickly that the optimal value of this LP is at least something. I want a certificate of a lower bound of optimal of the optimal value. Okay. Then actually it's easy to find a certificate and verify that. Why? Because suppose I want to set it up is at least 10. Okay. Then if someone like give me the feasible point x prime such that x satisfy both constraint here, this I can check easily. And like suppose that x prime is such that c times x prime is 10. Then I know easily that op is at least 10. Right? So the point is that there is an easy certificate for the lower bound of opt. Okay. Is there, what if I want some easy certificate for the upper bound of opt? That's my next question. And that's the motivation for dual. How can we show an upper bound of opt? If opt is here, again, to get any feasible point of LP will give some lower bound for opt. How can we find some upper bound for opt? And how can we verify that easily? Okay. So, okay. This is what LP duality is for. And let me start with some example before defining what it is. Like suppose this is your goal in mind, you want to derive some upper bound for the optimal solution. And let's say that we have this LP, the thing that we have from the beginning, this small LP here. Okay. Now I imagine that I'm gonna introduce some variable y to multiply to each of these constraint. And the first idea is that actually we can derive an upper bound by focusing on each constraint. Let's see how. Okay. Suppose that I want an upper bound from the first constraint. So I set y here, y1 here to be 2. Okay. So imagine that I set y1 to be 2 and multiply 2 from both sides. Okay. Then what do I get? When I multiply 2 y1 to this constraint, if you look at this thing, like this thing, just this multiplied by y1. Okay. But you see that this is what? 4x1 plus 2x1. This is the expression that dominates the objective. The objective here. It dominates the objective. It's always at least the objective, you see. So it's this expression upper bound the objective, always. Because this is upper bound because x is at least 0. Okay. But we also know that this thing is at most 2. Just because we know that as long as x1 and x2 is feasible, is in this feasible region, then this thing must be at most 2. So you know that this whole thing is at most 4. So from this, I conclude that opt must be at most 4. Question about this? If you're good, can you tell me? Do this or something? Okay, good. So you see that you can try to derive an upper bound just by making the constraint, making some constraint here to dominate the objective, and the constraint itself gives you some upper bound. Okay, yeah.
When you're getting this upper bound, you're only looking at just one constraint in this example.
In this example,
It's still an upper bound, but okay.
but it might not be the best upper bound. Yeah. So the better idea exactly is just to derive an upper bound from some linear combination of constraints.
Thank you. Yeah.
So imagine that instead of trying to multiply y1 to this constraint so that it dominates the objective, what if I just choose this combination y1 and y2, multiply to both of them so that the left hand side here still dominates the objective. Just try to find the best y. Okay. So that's suppose, for example, I choose y1 to be this, y2 to be this. Now I claim that as long as x1 and x2 are feasible solution, then the objective here of x1, x2 will be at most this thing. By choosing, I choose y1 here and y2 here, so that when I multiply to this, then coefficient wise, for each coefficient of x1 and x2 is going to be more than, coefficient of x1 here is going to be more than 3, coefficient of x2 here is more than 2. If that's the case, then I know that this upper bound the objective.
So we don't need to like actually find, like before when you're setting the lower bound, like we found like a point in the region, in the feasible region. We don't have to do that
No,
for this. Okay.
we need to find y
Okay.
such that when you multiply y to each constraint, then it dominates this thing. Once you find some yi, y1, y2 such that this is true, then you're good.
So we haven't talked about how we're finding y.
No. Okay. And once you find such y, then you can derive an upper bound because this thing needs to be at most 2 if it's feasible. This thing at most 6 if it's feasible. Now you get a better upper bound. Okay. So from here you get better but upper bound for opt. But by the way, recall that before that opt is at least 3.62. We find like some feasible point for x such that opt is at least this. So it basically match. The upper and lower bound match. And this is not coincident. So now here is a punchline. So you see that, okay, now our goal is to find y such that it gives us the best upper bound. The task, it turns out that the task of finding the best y here can be modeled as another LP. Okay, so let's see. Finding the best y is just another LP, and so you can solve it. You can find the best y actually. So look at this example, right? You have an LP. You want to find the best linear combination of constraints that gives the smallest upper bound. So let's try to write this mathematically. We want to do this mathematically. So I introduce y, try to multiply it here to here. What do I want to minimize? I want to minimize 2 times y1 and 6 times y2. Right? Because this is just like here. 2 times y1, 6 times y2. This is the thing that gives you upper bound. So we want to minimize this thing. Okay. What's our constraint? We need that when we multiply y1 to the first constraint, y2 to the second constraint, this whole thing dominates the objective. So this should be true for every x that is non-negative. And we also want that y is at least positive. Yeah.
Sorry, we have a polynomial time algorithm that solves a linear program, right?
Yeah.
So why do we care about getting a bound?
Yeah, so basically because we want to just learn this concept for our analysis, for our other things. Like we don't just care about how to solve the linear program. Yeah. And by the end, I tell you one more reason. Yeah. Yeah.
That constraint we have, does that need to be, is it okay that it's one line as a constraint, or do we need 2 constraints?
Right now, I just have this, but we're gonna derive 2 constraints.
Okay.
Yeah.
Sorry.
But basically, you agree that we want to find y such that when you multiply y, it dominates the objective here. That's what we want. And then I can rewrite it a bit. Just kind of, instead of having y like this, I collect the coefficient and then right now it's like this instead. Just multiply y to here, and rewrite. And I get this thing. Okay. And actually, what about this constraint? This constraint is true for all x that is positive. if and only if both of these constraints is true. That is, to have this is true, basically you need that the coefficient of x of x1 need to be more than 3. The coefficient of x1 on this side. The coefficient of x2 on left side need to be more than 2. The coefficient of x2 on the right side. So this constraint is just the same as having these two things satisfied simultaneously. So with this, now you can just say that this is what you need. And isn't it LP? This is an LP. And this is what we call dual of the dual LP. From the primal LP, you can derive another LP, which is this one, and we call it dual. Okay. And we can do this and by the way, I did this for like the primal LP, which is in the standard form. I want you to do this at home. It's quite important, by the way, because you will need to derive dual and on your own quite often from now. Suppose that the first constraint is not in the standard form. Suppose the first constraint is this instead, or is equality instead. Then try to derive the dual on your own, and then see that you're gonna get basically the same LP, the same dual LP, similar to this, except that y1 need to be at most 0 instead of y1 at least 0. Try to do this. Or if this is equality, y1 is going to be the same except that y1 is unconstrained, can be positive or negative. So do this just to make sure that you understand the concept. Okay, but let's do this for the general LP again. Okay, suppose you have the general LP in the standard form. Okay. I can rewrite it a bit so that like if AI is a ith row of A, AX at most B is just this thing, right? You have M constraints. For each constraint, you want this thing. Okay. And we want to find the best upper bound. We try to derive dual LP. So the way to do this is to multiply y to each constraint. We want to find the best linear combination. So we multiply y to each of this. What do we want to optimize? We want to minimize the best upper bound. So we want to minimize this thing. Okay. And what's our constraint? We want that when we multiply the y to this side, it kind of dominates the objective. So multiply the y to the left-hand side, it dominates the objective. We want this. And y are non-negative. Yeah, the reason why y is non-negative is because you have this constraint. If this is actually like at most 0, at least 0, then it's going to be non-negative. It's going to be like another way around, like this. Anyway, you have this. And I can rewrite. If A prime J is like the jth column of A, you can kind of, rearrange things here and you get this instead. I don't do this like, it's just you can verify this quickly, nothing going on. And now for this to be true, for all point x that is non-negative, it's just the same thing, this thing. It's just the same thing as saying that for every coordinate of x, you need that this thing is at least this thing. So you need all of this simultaneously. It means that you can replace this big line here with many constraints. That is linear constraint. And you basically get this thing, which is another LP. Okay. So now I can define the dual LP precisely. Yeah. for any LP P, the dual LP is just this thing. This is the definition, but you see like why like this definition is kind of justified by the motivation. This is the thing that we can derive when you want to find the best upper bound of this thing. Okay. And for example, this is an example that we saw. If this is a primal, this is going to be dual. Okay. And by the way, like if you start with primal here and you want to derive dual, you get this thing. And if you want to derive dual of this thing, you're going to get primal back. Yeah.
So is solving the dual equivalent to solving the primal?
So
Like if we get the answer for the dual, is that enough to get the answer for the primal as well?
the answer is yes. Although this is a deep theorem, like and like we actually will not prove this. We will prove this later in class. But it's going to be the case that although the solution here lives in like a n-dimensional space, the solution here y live in m-dimensional space. It live in the different space, but the objective, the optimal value, gonna meet actually at the same value, although they live in this different space.
Okay.
Yeah, you can try at home. Like I show you how to derive the dual of this thing, and you get this thing. If you start with like this LP, this is a minimization LP, so it's straightforward to try to minimize. So it's straightforward to get an upper bound. Just by like finding feasible point for minimization problem. Finding a feasible point gives you an upper bound. But what about if you try to get a lower bound of this thing? You need to try to find dual of this guy. When you try to derive dual of this guy, you're gonna get this one. It turns out. So dual kind of it's just like a kind of flip side of each other. And dual of dual is gonna be the same thing. Dual of this and dual of this kind of come back. That's why it's called dual. Yeah. Yeah, I stress again that dual LP are related to each other, but the solution on primal and dual, they live in different space. Just think like max flow and min cut, they're gonna be dual of each other. The problem of finding max flow, solution is like flow on each edge. For the min cut, is to find like a set of vertices. So it's like different object, but they have the same value. Okay. So now, yeah, once you take this as the definition of dual, let's try to confirm like let me state like a really important property of the dual LP. Okay. So the first is weak duality. This is a theorem that confirms that the definition of the dual really align with our motivation. That is, it gives an upper bound. What do I mean is that if you start with a primal LPP and you define the dual like this, then then you have that op of P is at most op of D. So the solution in the dual upper bound, the optimal solution of primal. Okay. And so like you believe this for sure because we just derived it. But let's see the proof that is super quick, actually, super simple. So the reason is that I claim that let's say x is any feasible primal point, primal feasible point, that is you have this thing, and y is any dual feasible point, that is you have this thing. Okay. So with this, so I have basically I can just write down a primal objective here, but this is going to be at most by this thing. You have that C is at most YA. C. But sorry, X. But AX here is at most B. So this is Y, B. This is primal objective. This is dual objective. So yeah, a dual objective always is at least primal objective. This is true for any point, and it's true for the optimal point as well. So if it's true on the optimal point, this is when, let's say this is x star, this is y star, the optimal point. This is just op of P. This is just op of D. So you have this. Okay, nothing surprising here. And yeah, again, if instead if P is a minimization LP, not maximization, and if D is dual, then we're gonna have instead that like D will low bound P. Yeah. Just the same proof. Just like think of this, rename this as P, rename this as D. Same proof. Okay. But now it's like the deep and powerful theorem, which says that, yeah, when they are not unbounded, when the optimal point exists on both of them, then the optimal value on both primal and dual are the same. This is like supposed to be like quite a big deal actually. It's not clear, but it's true. But we're gonna see why it's true. Like when we learn about this algorithm, that is like one of the coolest algorithms. Yeah, we're gonna talk about it soon. But it appears in economics, it appears in ML, it appears in biology, it appears in algorithm design. It's everywhere.
I don't know if this is like getting ahead of what we're talking about, but if opt exists for P, do we know that it exists for D, or is it possible that there's a solution for P and there isn't a solution for D?
Actually, good question. If opt exists for P, then it must exist for D.
Okay.
Yeah. And vice versa. Yeah. Okay. So take this for now. We prove later. But if you want to learn the proof, which is like a standard proof, you learn from this MIT course from our Uncle Moitra. I'm going to prove this in a very different way, using weight update. But later, okay. Okay, so inverse again. For any feasible primal solution and dual solution, you always have that the objective of primal at most objective of dual, and the opt of each of both kind of meet at the middle. Yeah. Okay. Okay. So I'm now gonna answer like a Scott question why this is useful, like why the concept of dual is useful. Okay. So So first thing is that we first can just know like an upper bound and lower bound just by solving it. That's true. But actually, to solve an LP is like a difficult task. It's really like not easy to get to the optimal solution. But now with the concept of this dual and the fact that we know that the strong duality is true, now like there is a very easy algorithm to verify that you have an optimal solution. Not to find it, but to verify it. It's like a kind of like a P versus NP, right? Yeah, that's it, that concept. If you want to just verify the optimal solution, that is easy. Why is that? Suppose that P is a LP, D is the dual of P. And let's say someone gives you a pair of solutions, X and Y, X for primal, Y for dual. Now, I claim that suppose that X and Y are indeed like optimal, but you don't believe it yet. You can verify this easily. You can verify its optimality. How? Like, you can verify without solving the linear program. So what do we need to do? We just need to say that check that X is feasible. That's easy. Just really multiply vector to matrix. Multiply X to A. And then check that Y is feasible. And then check that the objective meets from like the objective of X and Y are the same. This is all super easy computation. But if this is true, then you know for sure that X and Y, both of them are optimal solution. You agree, right? Because if not, like, if they are not optimal solution, there is no way that these two guys meet. Okay. Okay, questions? All right. Okay. So basically, there exists Y such that X and Y satisfy the above condition if and only if X is optimal. If X is not optimal, there's no way to find a Y such that this is true. Because if X is not optimal, this equality must be like inequality, strict inequality. Okay. Next, okay. So we will see soon that like dual LP is not just for obtaining upper bound. It will help us designing algorithm and help us prove theorem too. So like in the homework, you will like next homework you will like try to derive dual quickly, like given some like LP like the one from Xflow. How to derive dual LP of that. We will see this next class, but you will do some of that in your homework. But this is like a kind of cheat sheet that you don't need to go through the whole process that we did today, right? Like you know that if the primal is maximization, then the dual is going to be minimization, and for each of the primal constraint, you basically introduce the dual variables. This is like in here. For each constraint, you create one dual variables. Okay. And for each primal variables, it corresponds to one dual constraint. Okay, so here. primal constraint correspond to dual variables. Primal variables correspond to primal dual constraints. And if the LP is not in the standard form, like if the J's constraint is at most, this is standard form, so you get this. If the J's constraint is at least, then you get this. If it's equality, then it's unconstrained. If xi, the constraint like xi is at least 0, then you get that the ith constraint is this one. If at most this, you get this. If it's unconstrained, then the dual constraint is equality. You can try to like I think like it's good for you to try to think why this makes sense. Just by, for example, kind of go through how we derive dual in this class. Okay. And yeah, we will basically practice this together on next class. You see how to derive, how to prove Maxwell-Min-Cut theorem that we did just like immediately from duality of LP. So, okay, so that's it for today. And yeah, if you have questions, you can ask, but otherwise, yeah.
Are you going to release the statistics for the exam, like median or?
We will.
Okay.
We will, yeah. And also, yeah, good. If you want to look at your grade and want to like ask for regrade, you can come to like just email me and like come to my office. Okay. Yeah. So that's it. Yeah. Okay. See you.